Welcome to Group 2 Distillation. Let's meet the team.
Hi, I'm Andrew.
Hey, I'm Jacqueline.
Hi, I'm Navia.
Hi, I'm Matt.
Hey, I'm Linting.
In this presentation, we'll be talking about our distillation experiment to separate a water-methanol mixture. Distillation is a common separating technique in order to separate mixtures of fluids. This method takes advantage of differences in volatilities of components and repeatedly boils and condenses the mixture in order to achieve a desired purity. This distillation experiment requires knowledge from multiple chemical engineering courses, such as senior design, heat and mass transfer, thermodynamics, and even KEG 112. We were assigned this experiment in order to solve a theoretical problem in which a pharmaceutical company is cited for storing an excess of drums containing a waste solvent, which was a mixture of water and methanol. Currently, the pharmaceutical company has 50 drums of waste solvent in storage. However, the Delaware Environmental Protection Agency stated that the maximum amount of waste solvent in storage could be 40 drums. Additionally, drums are being accumulated at a rate of 3 drums per day. In order to solve this problem of waste accumulation, it was proposed that the solvent would be separated by distillation. However, in order for methanol to be sold, it must be 97% pure by weight. Additionally, in order for water to be safely and easily disposed of, the bottom stream must be less than 700 parts per million by weight of methanol. Luckily, the University of Delaware already has a distillation column designed to fix this problem. However, before operating the column, it was important to model this distillation. We used the McCabe-Thiele method and Aspen simulation to determine optimal operating conditions to achieve the desired purities. Additionally, we conducted a hazards analysis and determined different process safety features to be considerate of. After successful operation of this column, we were able to estimate the amount of product made as well as the profitability of this process and the duration of this project. There are many safety considerations to keep in mind during this experiment. For example, proper personal protective equipment must be worn. This includes long pants, closed-toed shoes, splash goggles, and nitrile gloves. Additionally, there are many heat hazards present during the lab, so when one might be exposed to these, they must wear proper heat gloves and the face shield when necessary. Additionally, during this experiment, a ladder must be climbed in order to reach the sample collection area on the first floor. During this climb, 3 points of contact must be maintained, as demonstrated in this video. In this lab, students were exposed to methanol, which is a flammable toxic health hazard. Additionally, its flash point is 52 degrees Fahrenheit, and its explosive limits are 6 to 36.5 volume percentage. In order to determine how likely it would be for methanol spillage to reach the explosive limits, a quick calculation was done. Assuming a 30 degrees Celsius lab and 100% pure methanol, it was found that 9.5 liters of methanol needed to be spilled to reach the lower explosive limit.
One of the secondary goals for this experiment was to draw and confirm the process and instrumentation diagrams for the column. Seen here is the schematic for the bottom half of the column, showing the bottoms tank, reboiler, and associated steam piping. Here we have the top floor P&ID, showing the remaining product, reflux, and feed tanks. These diagrams were an important resource during the operation of the column. Before any calculations or simulations can be done on the column, a mass balance was performed to solve for any unknown parameters in the system. The total distillate and waste streams were calculated for, along with the fractional recoveries of each component. With all of the stream parameters solved for, hand calculations were performed on the column using the McCabe-Thiele method in order to solve for the required number of stages, reflux ratio, and feed state. McCabe-Thiele is a graphical method that makes use of the liquid vapor composition graph for the specific system. First, a quality line was plotted from the feed composition to the XY line, and a minimum reflux ratio was found by taking the slope of the line intersecting the product composition and the point where the quality line intersects the XY diagram. This minimum reflux value is then multiplied by a safety factor and used to calculate two additional operating lines, shown in dotted red and black, that are representative of the different equilibrium conditions along the column. After these operating lines are plotted, tie lines can then be stepped down between the XY envelope and the operating lines to find the number of stages required for this system. Luckily, the number of stages was found to be 12, which is the same amount in the UD column. It is important to note that the results from the McCabe-Thiele model may not be completely accurate due to the many simplifying assumptions that are made. It assumes an ideal mixture at constant pressure as well as constant molar overflow. Constant molar overflow implies negligible heat loss from the column, negligible heat of mixing, constant heats of vaporization, and small sensible heat changes. It also implies that for every mole of liquid vaporized, a mole of vapor is liquefied.
To both solidify and add to the results of the McCabe-Thiele model, computations were run in Aspen+. Two types of distillation simulations were run, the first being the DSTWU block, which is a quick and simple method that uses similar assumptions as the McCabe-Thiele model, such as constant molar overflow and constant relative volatilities. The inputs to the DSTWU block are the number of stages, which in this case is 14 because Aspen counts the condenser and the reboiler, plus the 12 stages, the light key and heavy key recoveries in the distillate, which can be obtained from the mass balance, and the feed flow rate. The significant outputs to the DSTWU block are the minimum number of stages, the minimum reflux ratio, and the optimal feed stage. The minimum number of stages in this case is 7, which is a good sign because we have 13 stages in our distillation column. The second type of calculation used in Aspen was the RADFRAC block. This simulation is more rigorous and makes less assumptions than the DSTWU block. The inputs to the RADFRAC block are the number of stages, which is again 14, the reflux ratio, the distillate rate, and the feed flow rate. Significant outputs to the RADFRAC block were the product and bottoms composition, the temperature and composition profiles, and the condenser and reboiler duties. Because the product and bottoms composition were given in the problem statement, we set up variables for the reflux ratio and the distillate rate, and then Aspen iterated until we got the product and bottoms compositions that we desired. Through the iterations in Aspen, we found that the reflux ratio we needed to meet the composition standards was 1.42. As you can see from the table on the left, the distillate and the bottoms compositions were exactly what they needed to be to meet the standard. From the simulations in Aspen, we can see how the reflux ratio affects the methanol and water purities, as well as the condenser and reboiler duties. Adjusting the reflux ratio is definitely a trade-off. If you increase the reflux ratio, you get more pure methanol in your product stream and a lower methanol composition of water in the bottom stream. However, the condenser and reboiler duties go up, which increases the operating cost of your column, and you are collecting methanol at a slower rate out of your distillate stream. To ensure we meet the methanol composition constraint of the product stream and bottom stream, we need to operate at a higher reflux ratio than 1.42. We went into lab the first day with a goal of running the column at a reflux ratio of 1.75 so that we definitely satisfy the methanol composition constraints while also keeping the operating costs of the column relatively low. We also wanted to verify the DSTW model suggestion of the feed stage being on tray 6. We had the option to feed to trays 4, 5, and 6. We can see that feeding to tray 6 leads to more pure methanol and water in the product and bottom stream, and the condenser and reboiler duties go down. So in this case, it's not even a trade-off. It's cheaper and better just to set the feed tray to tray 6.
The startup and shutdown procedures were consistent for both days. First, LabVIEW was opened on the second floor computer, and then the cooling water was supplied to the condenser. To ensure the safety of operation, the operators verified that the emergency stop buttons were not pushed in and that all alarms in LabVIEW were enabled. All sight glasses were open for tank level monitoring purposes. With the assistance of the teaching assistant, the operators ensured that the composition of the feed tank and the reboiler were adequate for operation. Next, the compressed air was turned on to allow LabVIEW to control certain valves, and the seesaw valve was open to allow ventilation of the column. The steam valve controlled by LabVIEW was tested 3 times before allowing steam flow to the condenser. Hand steam valves are open to allow steam to flow to the reboiler. The steam flow rate was set to 100% to flush out any liquid water in the reboiler jacket. Once all liquid was flushed out of the reboiler jacket, the steam flow rate was set to 60% and condensate began to move up the column. When the condensate reached the top of the column, the vent was closed using the seesaw valve. Once the reboiler reached 75 degrees Celsius, a reboiler sample was taken. After all of this was done, the operators moved on to batch operation procedure. During operation, the column was first run as a batch process to allow the trays to reach an optimal temperature profile prior to continuous mode. The desired temperature profiles were 65 degrees Celsius for tray 12, 100 degrees Celsius for tray 1, and between 65 to 100 degrees Celsius for trays 2 to 11. This is because the boiling point of methanol is 64.8 degrees Celsius and the boiling point of water is 100 degrees Celsius, so having trays at these temperatures would allow for the most ideal separation. In batch mode, there is no feed to the column and there is no product or bottoms collected. Once the column reached equilibrium in batch mode, samples were collected from the trays and the reflux drum. The criteria for equilibrium was less than a 2.5 degrees Celsius deviation in temperature over a period of 10 minutes. The samples were analyzed with a densitometer at room temperature to obtain purities to ensure that the product line was at least 0.99 weight fraction of methanol and the bottoms was at least 0.95 weight fraction of water. Then the column was switched to continuous mode. For continuous operation, the valves to the product and bottoms tank were opened, the reflux was changed from total to partial, the feed tray was selected, and the valves to the feed tank were opened. Following this, the feed flow rate obtained from the Aspen simulation was inputted in LabVIEW. Changes were made in the feed flow rate, steam flow rate, and reflux ratio until the column trays reached the desired temperature profiles. Once the column reached equilibrium, samples were taken from the trays, reflux, reboiler, product tank, and bottoms tank. On day 1, the column reached equilibrium within 1.5 hours in batch mode without any changes made to the initial parameters. Once equilibrium was achieved, the column was run in continuous mode. The column in continuous mode showed signs of flooding and the trays were surpassing the desired temperature profiles. To counteract this effect, the reflux ratio was changed to 2. After observing no change to the temperature profiles after 20 minutes, the reflux ratio was changed to 2.25. While this change stabilized the temperature increase, action needed to be taken to decrease the temperature. Thus, the steam flow rate was once again reduced to 50% and the temperature profiles began to dramatically decrease. This change brought the temperature profile into the desired temperature range, but since it was made towards the end of the experiment, the column did not have enough time to equilibrate. On day 2, due to drastic changes in outdoor humidity and temperature, the column did not achieve the desired temperature profiles with the parameters used for day 1 batch mode. The column reached equilibrium within 10 minutes. Once samples were taken, the column switched over to continuous mode. Based on the results from day 1, the steam flow rate was decreased to 60% to counteract the expected increase in temperature. After 15 minutes, the temperature profiles were drastically dropping, so the steam flow rate was brought up to 65%. After 20 minutes, although tray 12 was at the desired temperature, tray 1 was exceeding its desired temperature. Therefore, the steam flow rate was reduced to 63%. After seeing no change in 15 minutes, the flow rate was once again brought down to 61%. This stabilized the temperature increase, and to decrease the temperature, the reflux ratio was brought to 2.5 and then 2.75 after 15 minutes. Once the desired purities were achieved, the column was shut down. To shut down the column, all steam valves were closed, the seesaw valve was reopened, and residual condensate was collected in the reflux drum. Once the reflux tank stabilized, all pumps were shut off, and all air valves, tank valves, and sight glasses were closed. The LabVIEW collection was also stopped at that time.
The results from day 1 were used to decide on values for the manipulated parameters to run the column on day 2. Additionally, from the day 1 data, We were also able to calculate tray efficiencies to use in our Aspen model. The day 2 parameters can be seen in the first table on the right. With the column running at these parameters, we were able to achieve methanol compositions that were well within specification. We achieved a methanol composition in the products tank of 99.8% by weight and a methanol composition in the bottoms of 300 ppm. We were also able to update the Aspen model by inputting the Murphy tray efficiencies in for each tray, inputting the pressure drop of the column, and adjusting the reflux ratio to 2.75, which is what we actually operated at. We were then able to compare the predicted composition and temperature profiles predicted by Aspen to the actual profile seen from the collected data. The model matches the data extremely well for trays 6 through 12, the rectifying section, and still decently well for the stripping section. The error of trays 1 through 5 most likely come from the steam flow rate being too high, which results in higher temperatures and more water in the lower stages. An important thing to note about these graphs is that the reboiler is denoted as tray 0 while the condenser is denoted as tray 13.
Something else we also did at the end of day 1 was calculating tray efficiency to including in our Aspen model. We chose the morphine vapor efficiency because it's defined for each tray according to the separation achieved. As the equation shows, it's a ratio of actual vapor enrichment to the ideal vapor enrichment, where the x is the liquid composition of the stage I, y star of x is the ideal vapor composition that can be found from y-x diagram. Y of x is the vapor composition on the operating line. Here is the mean result for efficiency calculations. The result for bench on day 1 shows 2 negative efficiencies on tray 7 and 10. The reason why is the higher measurement of X values on those 2 trays. After we paid attention on that, the result of bench on day 2 seems reasonable. For partial reflex, the efficiency from tray 7 to tray 11 are greater than 1. When the liquid on the tray is well mixed and is of the similar composition as the liquid in the downcomer leaving the tray, the morphine efficiency will be greater than 1.
Using the operating conditions from day 2, as well as the composition of methanol in the distillate and the bottoms, the total amount of product was found to be 0.07 liters per minute. Additionally, based on the current market price of methanol, it was found that about $15,000 could be made per year by selling this methanol. Assuming this distillation operation can be run 330 days per year, 24/7, it was found that it would take approximately 5.7 months until there are 0 drums left in storage.
So the ideal operating conditions we begin is the feed stage on tray 6, the reflux ratio 1.75 and the feed flow rate 0.3 liter per minute. After testing those conditions on day 1, reflux ratio increased to 2.75. The steam flow rate should be set to 60%. And the feed flow rate is gonna be 0.32 liter per minute in order to reach equilibrium more quickly. From those results, all drums in stage could be processed in less than 6 months. Furthermore, 0.07 liter per minute of distillate can be produced under those operation conditions, which yields a yearly revenue of $15,000. As some calculations we can draw from this experiment is, yes, this column is capable of doing this separation. At the given operating conditions, we can get methanol and water purified that are well above specification. And at this flow rate we used, we would solve the problem of having too much drums in stage. and we are able to handle the 3 drums we accumulated each day.
And a special shout out to Lucas for being the reflex to our distillation column.